Welcome back. So the next thing we're going to talk about is how the cell potential at E0 value relates to the equilibrium constant. And so it's really just a modification of the Nernst equation. So if you look at the previous video where we talked about the Nernst equation, that related that non-standard cell potential to the standard one using the reaction quotient, that Q value. So what happens at equilibrium? Well, that changes that Q value to a K value. And so what ends up happening is the Nernst equation with a little rearrangement becomes this right here. And again, this is just looking at that 25 degrees Celsius version of the Nernst equation. So all of those constants along with the this temperature in Kelvin boils down to this 0.0592. And so what we end up seeing then is that the logarithm of the K value, in this case I've got it as a log base 10, you may also see this equation slightly different but with a natural log. It's the same thing, you'll just see a slightly different constant value down here. But the log of that equilibrium constant is equal to the n value. Once again, what's n? That's the number of electrons being transferred in your reaction. So again, when you balance out the electrons gained, electrons lost, that's that n value. And then the E0 value, that's the standard cell potential for that process, divided by this constant. There's that same 0.0592. Again, that relates the Faraday constant, the 96,400 or 500, 486, I think it is there. And this has the temperature, 25 degrees Celsius or 298 Kelvin built into that. It's also got the R constant, that R value in there. So all a part of that constant right there. And so it relates those two things together. It's not something we use a lot because, as you'll see in the example we look at in just a moment, anytime that E0 value starts getting even slightly large, and for a large cell potential, you're talking like maybe around 1 volt. It ends up giving you incredibly large K values. All right, if it's a positive 1 E0 value there for that, you're talking about 10 to the 100th power for a K value. Essentially what that means is these redox reactions are pretty much completely product favored, that they really like to make products. Or when you start seeing negative E0 values that are again around 1 volt or larger, then those are almost completely reactant favored. So kind of the flip side of that. All right, so let's just take a quick look at this little triangle here that relates K, delta G, and the E0 cell. So some of this is from back in chapter 16 when we were talking about cell potentials, where delta G is equal to minus RT times the natural log of K. There's also a log base 10 version of this equation. It just includes a 2.303 transfer conversion factor in there between natural log and log base 10. And so here's the one that we figured out earlier in this chapter, that delta G is equal to minus NFE. So the N again is our number of electrons, F is that Faraday constant, and E0 is the standard cell potential. So it relates those two together there. And finally, this is again just another restatement of the one that I just showed you, that just rearranged and in terms of natural log, but again it works the same way. E0 of your cell is equal to R times T. R is the gas constant, 8.314. T is your temperature in Kelvin, make sure it's the Kelvin temperature scale, divided by N, your number of electrons transferred, and the Faraday constant. All of that ratio there multiplied by the natural log of your equilibrium constant. So again, it just shows you how all three of those are related to each other. All right, so let's just take a look at a real quick example here. I'm not even going to go onto the whiteboard with this one. So this is that same system that I looked at in the Nernst equation example here. We got a couple of silver ions making mercury, or reacting with mercury to form elemental silver and this mercury plus 2. And I'm not going to worry about the concentrations here for this one. We just need the standard cell potential for this. Remember, this one was a reactant-favored system, so it had a negative 0.055 volts standard cell potential. And then the number of electrons transferred was 2. There's 2 silver ions, each one gaining 1 electron, so 2 electrons total being gained by the silver, and the mercury is losing 2 electrons to form that mercury plus 2. So each single mercury ion, or mercury atom rather, is losing 2 electrons. And so 2 is our number of electrons being transferred. So then it's just a matter of plugging that into the equation. So here I'm back to that log base 10 equation. The log of k is equal to, there's our n value, 2. Here is the E0 value for this reaction, that negative 0.055. Again, we figured that out in the previous one. And then divided by that 0.0592. So that comes to a negative 1.86 when you get that ratio. That's equal to the log of k. How we reverse that log function, we take 10 to the x power of both sides. So the 10 raised to the log k, the 10 and the log cancel each other out. That's going to give us just k. And then over here we take 10 to the negative 1.86 power. And that's how we get this value right here, about 1.4, 10 to the minus 2. All right, and so again, that all fits with everything else we've been saying. When we have a negative cell potential, that indicates a reactant favored, a non-spontaneous electrolysis reaction, essentially is what that refers to. That would give us a positive delta G for that reaction system, again, indicating non-spontaneous or reactant favored. And to tie it all together, we get this K value that's less than 1. Remember, the crossover number for K is the number 1. Greater than 1 is product favored, less than 1 is reactant favored. So here, this is a reactant favored system with that K value just slightly less than 1. Even then, it's a lot less than 1. It's a factor of about 100 times less than 1, 10 to the minus 2 for that. And again, that was just with this barely non-spontaneous cell potential, this negative 0.055. That's a really, really tiny cell potential. That'd make for a really lousy battery system. Again, we messed around with the concentrations. With these two concentrations, we made it just barely positive in that previous example, if you look back at that. So anyway, just very, very small positive or small negative cell potentials typically result in still relatively large, factors of 100 greater or less than 1 for your K values. So just small changes in that standard cell potential can result in very large or very small K values for a particular reaction. So that's just a real quick summary. Again, like I said, we don't do a huge amount with this because we end up with these crazy large or crazy small K values. If you take a look in the textbook, it talks more about this and how, again, with just a cell potential around 1 or 2 volts, that results in a 10 to the 100th power K value, which again, for our purposes, that's pretty much a completely product-favored reaction. All right, so that's it for this one. I'll see you in the next video.